CSIT branch. Today my AAT Tech Talk topic of discrete mathematical structures is exact formula, improved bounds for general sum connectivity, index of graph operations. An abstract of this is PA molecular graph 0. The general sum connectivity index is denied as 0, and these are some of the equations where 2r and dov denotes the degree of the vertex v in the molecular graph 0. The problem of finding the best possible upper and lower bound for certain topological index is the fundamental nature in extreme graph theory. Akhtar and Imran obtained the sharp bounds of the general sum connectivity index for four graph operations and introduced by Elise theory. In the paper, we could and improved the sharp bounds of the general sum connectivity index for F-sum graphs. Several examples are presented to elaborate and compare the results of the improved bounds with existing sharp bounds. In addition, we obtained the exact formula of general sum connectivity index for F-sum graphs, where F is equal to S. Introduction. Let me show you the PDF. And this is the PDF where we can see the abstract, and this is the formula. It is defined as a summation of this. The index terms are the molecular graph, topological indexes, Cartesian product, total graph, F-sum graphs. An introduction of this topic is assume T is equals to Vt be a simple connected and finite molecular graph. We denote vertex set and edge set by Vt, and Et is more than Vt and the product respectively. The order and size of graph is denoted by modulus of the Vt is equals to n and the modulus of Et is equal to m respectively. Each vertex of this molecular graph represents the atom and each edge depicts the bonding of the two atoms. The degree of the vertex V, and symbolized by dgv, is the number of incident edges with V. A path graph or linear graph Pn of the length n minus n be a graph consisting of the vertex of the size V. Vi is I equal to 1, 2, 3 and so on up to n, and edge set is Vi plus 1, and whereas I equals to 1, 2 to the n minus 1. And the molecular graph to illustrate the constitution of the molecular structure where vertices correspond to atoms and edges to the covalent bonds between the atoms. The topological indexes Ti is a numerical quantity computed mathematically from parameters of the molecular graph and correlates the meaningful of the information. Various types of the valency distances. Various types of the valency distances, spectral and counting polynomials related to TIs of these molecular graphs are proposed in literature. However, degree related to which TI are extensively investigated due to their significance. To conduct QS or QSPR analysis, topological invariants play essential role to better understand the complexity of molecules. Psychochemical biological properties of corresponding chemical components. First is Zagreb and second Zagreb indices are among the pointed here were introduced by Gutman and Trinsaker denied as. Then this is the formula for the above. Li and Zheng extended the concept of the first Zagreb index and provided the idea of the RS general Zagreb index, which is given by this. And Milan Randick introduced a TI with the name branching connectivity index 12. It earned high rank in the chemical graph theory due to the application nature of its given formula. And this is the given formula. The introducer TI. The additive version of Randic index is known as some connectivity index, which is initiated by Zo and Transistic, and its formula is given by the below one. In 15, Zo and Transistic presented the concept of the general sum connectivity index and established the Northern Gadium type results of GSCI. The significance and effectiveness of the GSCI can be witnessed by its relation with the diverse TIs. Is the RS Zagreb index, is the hyper Zagreb index, is the harmonic index, and is classical sum connectivity index. Chemical application and mathematical properties of these indices are investigated and presented. Now we state two important results from basic mathematics which will be used in main results. And these are some of the basic graphs of the C6 along with its derived graphs. Let me show you some of the PPT. This will show you the PDF. And this is the, here we can see the all the formulas. And the results and discussion. And here are the basic graphs C along with its derived graphs. For a connected simple graph T, the subgraph divided the triangle parallel line superposition and the total graph can be instructed as follows. ST is derived from the base graph T by replacing an additional node on every edge of T. RT is achieved from ST by connecting the end vertices of the original edges of T that are incident with thin vertices. QT is attained by ST by linking those pairs of new vertices by edges which have common adjacent vertex. TT is constructed from ST by applying RT and QT simultaneously. And the result and discussion. In this section, the main results regarding general sum connectivity index of F sum graphs T1 plus S, T2 plus S, and here is the derivation of this formula. And we are using the binomial theorem. And this is the full derivation of this. We can see the full derivation, and also here are the some of the examples. And the applications and conclusions are results of the cycle CR and CS. Let CR and CS be two cycle graphs with vertices R and S respectively. The GSCA of F sum graphs is given here below, and also here they given the results for path PR and PS. Now let's jump into our conclusion. The sharp bonds for certain topological index is always an intricate and interesting problem. Sharp bonds for GSCA of 4 operations on graphs 1 CS02 were presented. In this paper, we proposed improved as well as pursues version of lower and upper bounds of GSA for F sum graphs, where F2. In addition, we derived exact formula for GSA of graphics and presented some examples. To conclude, we elaborated and compared our improved bonds with sharp bonds by taking tiny examples. In D2 and D3, our bonds involve order size, smallest degree, largest degree of 0, and certain eminent of TIs of the basic graphs, whereas sharp bonds involve order size, smallest degree, and largest degree of 1. Only as a consequence, only can observe one can observe and analyze that our results perform equally well for any kind of parameters, while the sharp bonds deviate from exact value for large values. And here are some of my references of the given topic. Thank you.